as we get ready for example 4, and specifically looking at the square root function, one of the things that we want to notice is that this square root function is different from the previous two because it doesn't have y-axis symmetry. So it's not going to directly match up with other points on across from the y-axis. So our key points, we see that there's one at 0, 0. We know we cannot take the square root of a negative, so we're focusing only on positive x values. We'd like to pick values you can easily take the square root of, so the square root of 1 is 1. The next easy value to take the square root of in terms of integral value, that means that it's an integer value, is the square root of 4, which is 2. So that's where those key values come from. Now, as we prepare for example 4, one of the first things I want to notice is that there's a negative multiplier on the x. This reminds me personally quite a bit of yesterday's examples, specifically even example 4, where there was a negative multiplier on the x inside the function. So as we go through this example, if you have any questions, you might consider reviewing back on example 4 from yesterday's notes. So the first thing we did when there was a negative multiplier is we reordered the function so that we would have a better chance at identifying the shifts. So we put the x first. Then we wanted to make sure that we could see the b as being factored out. So we take and factor out that negative 1, which means that the 4 has to change as well, because a negative times a negative will get you back to the positive 4 that you have. So what that allows me to hopefully see is that this value right here is my b value of negative 1. And then I can also identify my shifts. So I see a 4 inside, so that's a c value, and a 1 outside. But since it's negative and my formula usually has a plus there, I want to make sure I indicate the negative 1 as well. We're not often grading you on the A, B, C, and D, but knowing that it was negative is going to help you appropriately identify that that is a vertical shift down 1. We know that things inside affect the x, so this will be a horizontal shift. A positive 4 might make me think I was moving to the right, which means I'm really moving. So excuse me, I see a minus 4, which might make me think to the left, when in fact I'm really going to move to the right 4. Then we need to identify that our b was negative 1, which we know multipliers act as reflections when they're negative. So this is going to be a reflection over, since it's inside it has to change the x. In order to change the x, it has to go over the y-axis. And as long as we're at it, we should go ahead and acknowledge that there's no multiplier out front, so our a value is 1. As we go to make this graph, again, the reflection has priority. The reflection happens first. So in our mind, instead of going to the right and up, we should go to the left and up. So our initial thought is that our graph reflected should look like this. Now you notice I made it dashed and light so that if we need that visual confirmation, we kind of have an idea on what it's going to look like. You are not required to make the dashed graph at this time. You can go straight to the final graph. From there, we want to take our key point at 0, 0 and go right 4 and down 1. So I want to count right 4 down 1. And then I want to follow the pattern of points, but remembering that it's been reflected. So instead of going right and up, I need to go left and up, based on this particular reflection. So I'm going to go left 1, up 1, and left 4, up 2. Then I'm going to connect them carefully. If I ever want to double check that my points are been graphed properly, I can take the points on the transformed graph, the purple one, and test them in the equation. So for example, here's an x value of 0, 1, I believe is a point on this graph. So if I were to put a 0 in for x, 4 minus 0 is 4, the square root of 4 is 2, 2 minus 1 is in fact the y coordinate, which is what I need it to be. And example 4 is complete.